A very good morning to the chairman, Dr. Noor Amal, reviewer 1, Dr. Muhammad Zamri, reviewer 2, Dr. Uday, and to all of you who are watching this video. Thank you for your time. I'm Zhuo from School of Mechanical Engineering Materials Program. And let's begin with my undergraduate project title, A Prediction of Microstructure and Mechanical Properties of Cooling Slope Casted A17KM0062 magnesium alloy made by semi-solid processing. This project was initially going to carry out experimental work. However, due to the pandemic, I had to change it to become a prediction. This is the outline that I am going to present to you. A17KM0062 is a magnesium alloy with 9% of aluminum and 1% of zinc. It is widely used in various industries, including automotive, aerospace, and especially in the biomedical industry due to its biocompatibility. When using as an implant, A17KM0062 magnesium alloy can dissolve in human body fluid over time and no surgery for removal is required. And as we all know, microstructures of metal alloy exist in the form of dendritic structure. These dendritic arms are large in grain size and impurities are concentrated in the dendritic structure. This causes the limitation in mechanical properties and castability. Semi-solid processing is a manufacturing technique that can process metal alloy in slurry form and solidifies the particle into globular shape instead of dendritic shape, with smaller and uniform microstructure. The advantages includes increasing die life, reducing grain size and solidification shrinkage, reducing gas porosity, and most importantly, improving mechanical properties. Cooling slope casting is one of the most popular semi-solid processing methods. It is the simplest semi-solid processing setup, which consists of only a furnace and a sliding slope for cooling metal slurry. Its casting parameters include pouring temperature, cooling slope length, and slope angle. The working principle of cooling slope casting starts from metal alloy is superheated in the furnace and melted in molten state, and the molten is left cool to the desired pouring temperature, which is slightly above the liquidus temperature. The molten is then poured to the cooling slope to flow through the slope into the mold. Throughout the flowing process or the slope, the shearing action between the slurry and the slope will break dendrite arms from the mother dendrite and further grow into globules. Human desires are unlimited, from only simple functionality to better performance and better durability and even better appearance, but the resources are limited. From pure metal we have foam alloy and even composite. Conventional casting has reached a plateau in materials engineering. Metal dendrite is causing brittle fracture. Engineers are trying hard to find better ways to produce a material with higher strength and also a more shapeable material. Cooling slope casting can produce semi-solid metal with higher strength and castability by producing a finer and uniform grains. The objectives of this project is to investigate the effect of cooling slope casting on mechanical properties and microstructural properties of S-cast magnesium alloys, and to investigate the effects of different cooling slope parameters, for instance, the pouring temperatures, cooling slope length, and cooling slope angles. The scope of this project includes cooling slope casting of A17KM0062 magnesium alloy, review the effect of cooling slope system on the microstructure changes and the mechanical properties of this alloy, to investigate the effect of cooling slope system with various melting temperature, angle of slope, and pouring distance, microstructural investigation of S-cast sample using optical microscopy and scanning electron microscopy, and lastly to investigate the mechanical properties of S-cast sample using tensile test and Charpy test. And we move on to methodology. And the first step is to cut the A17KM0062 ingot into smaller pieces to fit into the furnace. So from this 8 kg A17KM0062 ingot, we cut using power sawing machine at P23 UTM, and we cut into smaller pieces to be able to fit into the furnace. Now we move to the second step, to cast. So the molten is left cool to the pouring temperature with different pouring temperature, and the pouring temperature is poured onto the cooling slope to flow using different cooling slope length and different cooling slope angle. And lastly, the molten is collected in a permanent mold. So this is the cooling slope casting setup. So first we superheat the A17KM0062 magnesium alloy in the furnace, and then left cool to the different pouring temperatures that we set. And then the molten is, after reaching the desired pouring temperature, the molten is poured onto the cooling slope. The cooling slope range varies from 300, 400, and 500 millimeters, and the cooling slope angle can vary from 30, 45, and 60 degree. We can control the cooling slope angle by this tilting mechanism. After done casting, we perform mechanical testing. The first one is tensile test. So we use a lathe machine at E01 to machine the specimen into the required geometry by ASTM standards, and then test tensile test using the universal testing machine at E04. The second mechanical test is the HRP impact test, which measures the impact force that absorbed by the specimen before fracture. So first we use EDM wire cutting machine to machine the specimen into required test specimen geometry, and then we use high energy falling weight impact tester to perform the HRP test. The final step is to perform materials characterization. We are using optical microscopy, SEM, and XRD analysis. So this is optical microscopy, SEM microscopy, this XRD machine at T05. And we move on to result and discussion. Before the lab closure, I am able to carry out the experimental work until halfway. So this is the incomplete experimental result. So we have 3 different casting parameters with each have 3 different values. So it's a 3 factorial to a 27 sets of casting parameters. And the R1, 2, 3, and 4 is the reference. And this is the result. You can see the result is fluctuating from here, and the stress strain graph. The fluctuating is contributed to the fluctuating of results is contributed by the casting defects, which acts as a stress concentration factor. You can see porosities appears randomly all over the specimens, which produces an inaccurate results. So due to the pandemic, I'm unable to further carry out my experimental work, so I make predictions according to the previous work. However, there is no work performing cooling slope casting of A17KM0062 magnesium alloy yet, but there are plenty of cooling slope casting of aluminum alloy. So I will use the outcome of cooling slope casting of aluminum alloy to predict the outcome of cooling slope casting of magnesium alloy. So first I compare between the both alloys microstructure to find the similarities. So it turns out the microstructure of the A17KM0062 magnesium alloy is expected to behave the same as the aluminum alloy throughout the cooling slope casting, and this may result in the same shape factor after cooling slope casting because they have a very similar microstructure, as you can see from figure 24. And first we look at the effect of cooling slope casting on microstructures. From figure 25, without cooling slope casting, you can see the microstructure is in dendrite structure, and with cooling slope, the dendrite structure has converted into globular structure. This globular structure is quantified by using equation 2, the shape factor equation, into the shape factor. So when shape factor equals to 1, it means a perfect circle. So closer to 1, which means the globular structure is more round and more circle. And the results are summarized in this table. From conventionally cast the 0.18 shape factor, we can get up to 0.75 shape factor. And this is the previous work to study the effect of pouring temperatures. So when using a low pouring temperature, we obtain a smaller grain size and a higher shape factor. And these results, these microstructures image are summarized in and quantified in this table. And note that the initial grain size is the conventionally cast without cooling stop casting. So after cooling stop casting, the reduction in percentage will be used to calculate, to predict our cooling stop casting of SG91D magnesium alloy. The shape factor is assumed to be the same because the both alloy initially share the same microstructure. And to predict the outcome of cooling stop casting of magnesium alloy, first we need to determine the range of pouring temperature. So we can't use the set of pouring temperature in cooling stop casting of aluminum alloy. This is because different materials, they have different liquidus temperature, and the pouring temperature is supposed to be slightly above the liquidus temperature to maintain at a low superheat. And we obtain the liquidus temperature of SG91D magnesium alloy from the DSC curve, and we apply the similar margin above the liquidus temperature to get this range of data. And we apply the similar percentage of reduction in grain size to predict the average grain size of choosing different pouring temperatures, and the shape factor is assumed to be the same and is graphically presented in this figure 29. And when a low pouring temperature is used, we obtain a smaller grain size and a greater shape factor. This is because when pouring temperature is high, the slurry remains at high temperature for flowing down the slope. The formed globular nuclei might dissolve back into the melt. And we move on to effect of cooling slope length. So from these images quantified into this table, and we get a result of longer cooling slope length can affect in smaller grain size. So to make the prediction of cooling slope casting SG91D magnesium alloy, we use the same slope length, and we use our pouring temperature, and we apply the similar percentage of reduction in grain size. And the result is presented graphically in figure 31. And with longer cooling slope length, we have smaller grain size. You can see the trend going low. And with longer cooling, this is because the shearing action between the slurry and the slope carries out longer. The formed globular nuclei are able to refine further down the slope and resulting in smaller grain size. And we move on to the third cooling slope casting parameters, the cooling slope angles. So this previous work uses two different angles, 45-degree and 60-degree, and this is the result. The degree of sphericity is also known as the shape factor. It is the same thing. So from here we can see with 60-degree slope angle, the shape factor is higher and the grain size is smaller. And applying the similar percentage of reduction in grain size, we predicted these results and this graphical result. And with higher cooling slope angle, we obtain a smaller grain size and a higher shape factor. This is because with a more slanting angle, the slurry experiences more gravitational pull down the slope. The shearing actions between the slurry and the slope are stronger, and hence a greater number of refined nuclei can be formed. And we move on to the improvements in mechanical properties. Figure 37 shows the relationship between shape factor and mechanical properties. As you can see, as the shape factor approach to 1, the ultimate tensile strength and elongation are getting higher. So you can see after cooling slope casting to 0.75 shape factor, the improvement in ultimate tensile strength has grown 25%, and the improvement in elongation is 67%. By applying these improvements, we predict when we cooling slope casted SG91D magnesium alloy to become 0.75 shape factor, we can obtain 288 megapascal of ultimate tensile strength and 8% of elongation. This is to compare between the conventionally cast SG91D and the cooling slope class Z91D. And then we compare the predicted data to other data of semi-solid Z91D magnesium alloy. So this is not produced by cooling slope casting, but with other semi-solid processing methods. So you can see there's a slight difference between the predicted data, and the difference could be due to the difference in different semi-solid processing methods, or the prediction could be incorrect, and it is yet to find out until the experimental results is established. For the Sharpie impact test, there is no previous work on performing it yet. But based on the advantages of semi-solid metal alloys, the impact absorbed by the cooling slope casted Z91D alloy is expected to be higher than the conventionally casted alloy. This is because semi-solid metal alloy has a finer and more uniform microstructure to have a greater mechanical strength compared to conventionally casted metal alloy with dendritic microstructure, which the dendrite is acting as a stress concentration factor to break easily. And we move on to chemical compositions and the phase changes analysis. This is to analyze the effect of cooling slope casting on the chemical compositions and the phase changes. So from the result, it shows very little change in the content of the alloying elements, which the semi-solid Z91D alloy is being well between the specification of Z91D alloy. So it doesn't create a big change in the chemical compositions. So from the XRD result, the results indicate that only the alpha magnesium phase and the beta magnesium aluminum phase were present in both samples, and no evidence for the presence of any other phases was detected by the XRD analysis. So with all of that, we can conclude cooling slope casting can alter the microstructures of the Z91D magnesium alloy, transforming its dendritic microstructure into globular microstructure, or for a smaller grain size and a more uniform microstructures, and so to improve the mechanical properties of the alloy to become stronger and more ductile. Secondly, the different cooling slope casting parameters can produce different results. The best results can be obtained in cooling slope casting of Z91D by using a low superheat pouring temperature slightly above the liquidus temperature, which is 590 degrees Celsius, a longer cooling slope length, 350 millimeters, and a more slanting cooling slope angle, 60 degrees. And thirdly, cooling slope casting does not produce any significant difference in chemical compositions and phase changes. And there are a few recommendations for further study on this topic. First is to continue the experimental work to prove the prediction data. And second is to find the reason of the porosities and improve the setup to produce more accurate results for the experimental work. And the third is to include isothermal holding or heat treatment process after cooling slope casting to further improve the properties of Z91D magnesium alloy. And this is the UGP2 gun chart, and you can see this is planned but didn't finish, and this is unplanned but finished. And the references and acknowledgements: my supervisor, Dr. Wan Fahmi Faiz bin Manali; my co-supervisor, Professor Dr. Muhammad Hasbullah Haji Idris; and I'm working with a PhD student. His name is Rijan Kamal. And appendix. Finally, thank you to all the panels for your time to evaluate my work. Thank you.